Hello all, my name is Nico Dreyer and today I will be talking with you about our first physics project. I would just like to say before this starts that yes, it is only me doing this because my group never responded to my email, so I was like, okay, I'll go ahead and do this on my own. So, the beginning. This initial slide describes the problem that we were given. Initially, we were given the acceleration in both the x and y directions as components and the initial time of launch at t is equal to a negative capital T. And we were asked to find how much time the helicopter is in the air as well as where it lands, and the horizontal direction for where it lands would be denoted by lowercase d. There are not many complex assumptions when initially creating the setup for this problem. They are listed on this slide, such as that the acceleration remains as represented, the helicopter should land at a measurable distance, d, and that there is no air resistance as a factor in this problem, because if there was air resistance, that might skew the equation in the x direction, especially when determining d. Also, the unknown quantities of this problem are capital T, some time variable, the constants alpha and beta, which I will later solve for, and also anything that we are solving for, such as the horizontal distance. This model represents our initial situation along with corresponding graphs for both the x and y accelerations. I created these graphs based on the lowercase t value. For the x direction, it's not squared, and therefore the graph must be linear, as shown off to the left, and for the y direction, the lowercase t value is both to the power of 3 and 5, so the graph must curve exponentially somehow, as represented by the acceleration in the y direction after I graphed it on Desmos. Also initially, the capital T is negative, so I used basic math to figure out the end behavior of each graph and represented this within the diagrams depicted. Some useful information. I know that from the problem setup, I can easily take and determine the integral of acceleration with respect to lowercase t in order to find both velocity and later position. Initially as well, I know the time is some value in negative capital T when the velocity is equal to 0 for both the x and y directions. Using this logic, I can therefore denote the ending time when the velocity would ideally be equal to 0, which is another assumption, again, as a positive capital T to show the passage of time and make solving this problem more manageable. Now, in order to find the corresponding position function, velocity was integrated with respect again to lowercase t. In order to find the actual position, negative uppercase T does not need to be plugged in, but rather positive uppercase T, as denoted before, which was defined when the velocity again reaches 0, hopefully at the end point of the helicopter's journey. These values are found above, one of which is d, the answer to the horizontal change in the position of the helicopter, and it's denoted by 2 times beta times capital T squared divided by 3. And the change in position in the y direction is denoted by 2 times alpha times t squared divided by 105. It's a big number. Now, in order to make sense of this problem and solve for the distance as it corresponds to the y direction and make sense in the terms of units we're given, I solved for t squared in the x direction, which turned out to be the square root of 3d divided by 2 beta, or t squared is equal to 3d divided by 2 beta, and plugged it into the y value for t squared. This gave me a value, and as shown on this slide, that marks the total position as a change in y as well, which hopefully solves the problem. I then wanted to find out what beta and alpha were, so I plugged in pure units into my known equations and calculated that beta and alpha are both units of acceleration, or meters per second squared, which is really useful. Now, this slide is just sense-making. The units in my final x direction were meters, which makes sense as I plugged it in. The units of my final answer in my y direction were also meters, which makes sense. The units of capital T, regardless of sign, was seconds, which is self-explanatory because lowercase t being equal to capital T as an initial setup means that t would have to equal seconds. And finally, solving for the units of the unknown constants of beta and alpha. They are both meters per second squared and acceleration units. This means that both beta and alpha, as constants that are now unknown to me, are both slope units of my position graphs, which I will later go on to show you. And now this is a real-life example problem. So for my example problem, I chose to plug in a time value at t is equal to 10 seconds, because why not? The acceleration in the x direction or beta is equal to 7 meters per second squared, and the acceleration in the y direction of 10 meters per second squared, just the opposite of gravity, just for fun. I plugged these numbers into my functions and was able to get my distance traveled horizontally, d, and vertically, the change in the y direction. This part of the problem made me realize that the equations given and derived depend a lot on the values chosen for beta and alpha, or the slopes of the graph, and x and y accelerations respectively, and that if the helicopter is accelerating more towards the x direction, the height will decrease because of the d in the y equation that I eventually ended up solving for, and the beta being on the bottom in the y direction. And if the helicopter is accelerating more in the y direction, the height will generally increase because that's just how the problem setup works. Additionally, the vertical distance traveled by the helicopter is dependent on the distance it travels horizontally as well, due to plugging in the value solved for t in the y position equation. Because I plugged in a y value for capital T squared into my change in y direction, the resultant height of the helicopter will be primarily dependent upon x, or the change in position of x rather, as seen in the example that I'm showing here. Now, finally, I would like to show you the position graphs that I created as a result of the functions derived in the previous part of the problem before sense making. Represented above is the model I created for final position functions in both the x and the y directions. The graph of d, or the horizontal change in position, is a cubic function after derivation, but I chose to start this function at the origin with x is equal to negative t, meaning the curve that is cubic will be shown as more of a downward-facing parabola from the initial x is equal to negative t to my x is equal to final t, the ending time. In the y direction, the function is more complicated with a value of t to the fifth being included, but graphically, it is a parabola that is some fraction of the total position derived, as shown before when solving for the change in vertical position. The time at which the helicopter ended its journey is also denoted by a capital T, as shown above, which was derived from the horizontal change in position and is relative to the horizontal distance as well. T is a value that is equal to the square root of 3 times the d, or the horizontal position, divided by 2 times beta, or the acceleration, in the x direction. Now finally, for my reflection. This problem is in part similar to Homework 3, Problem 3, which included solving the x position function for a time value and plugging that time value into the y position function in order to get the complete answer. Also, in that corresponding homework problem, integration was needed in order to solve for the final time and position of the penny as it flew through the air in the elevator, which was the problem. All motion problems generally have the same setup and requirement for integration, which is why these problems are fairly similar. Additionally, this problem entailed solving for the change in vertical position as a function relative to the x direction traveled, meaning that vertical displacement traveled is dependent not only on time, or capital T, but also on the horizontal position traveled, denoted by d. Finally, both the x and y components for position depend also on the values inputted for beta and alpha, the accelerations in both directions, which were constants that remain constant throughout the integration. This problem overall presented minimal challenges in terms of actual solving and work, and was easy to explain and come up with the reasoning and graphs for. It would have helped to have 2 other group mates, but I tried to do the best with the circumstances given, and believe I came up with the proper result overall. Thank you for listening.